Good morning, students.
Good morning, sir.
Good morning, sir.
Okay, we'll now continue with the lecture. In the chapter 3 on relativistic dynamics, I already mentioned what is the dynamics. In mechanics, if you take into account the force acting on the body, then it is called as the dynamics. Then we will take up what is called as longitudinal mass and the transverse mass first, and afterwards we will take up what is called as twin paradox. Now, uh, in the Newtonian mechanics, which you have studied, 11th standard, then first year BSc, the direction of the force and acceleration is same. So whatever the direction the force is applied in same direction, there is the body is accelerated. So force and acceleration have the same direction. Now let us see what is the meaning of this. See, in the Newtonian mechanics, force and acceleration have the same direction. Let us see the meaning of this. Suppose the body is moving with a certain velocity in a certain direction. Then, if we apply the force in the direction of velocity, then the velocity of the body will increase. See, if we apply the force, exert the force on the body in the direction of its motion, direction of the motion means direction of velocity, then the velocity increases. Velocity increases means it is accelerated. So the acceleration now is in direction of the force. So since the velocity increases, that acceleration is positive. The final velocity minus initial velocity, acceleration is positive. That means direction of force and direction of acceleration is same. Now, suppose the force is applied in the direction opposite to that of the velocity. So you are applying the force in the direction opposite to that of the velocity, in opposite direction of the motion. Then velocity.
Excuse me, sir.
Hello? Hello?
Sir, are you sharing your screen, sir?
Yes. You can't see?
No,
Sorry.
sir.
We can't see.
No,
Okay.
sir.
Okay. Okay. Now you'll able to see it. No problem. this is the slide which I was talking about, that what is called as relativistic dynamics. Okay, so I was mentioning that the force and acceleration have the same direction. If the force is applied in the direction of motion, then the body is accelerated. So the force and acceleration have the same direction. If the force is applied in the direction opposite to the motion, then the this velocity decreases because the force is applied in a direction opposite to the motion. So velocity decreases. That means it is deaccelerated. So here also that deacceleration, it slows down. So deacceleration is in the direction of the force. So in both the cases, the force and acceleration have the same direction. Now that is in the Newtonian relativity. But in the Einstein's relativity, the force and acceleration may not have the same direction. So this we are going to prove that force and acceleration, the direction may not be same. And there are only two cases where the direction is same. So there are two cases the direction is same, and one case is when force is in the direction, the force is in the direction of the velocity, and that is called as the longitude. The mass corresponding to that is called the longitudinal mass. And another case is the force is perpendicular to the velocity. So in this case, the corresponding mass is called as a transverse mass. So this is the literal meaning of that. Longitudinal means parallel. Transverse means perpendicular. Now all these things we have to see by deriving the relation. Okay. So first we will take up what is called as the longitudinal mass and the transverse mass. Okay. So see here, we will consider Newton's second law. If we consider Newton's second law, the force is rate of change of momentum. See, what we are saying is that suppose the particle is at rest. Particle is at rest. Its mass is m0, and that's what we have seen. We have seen yesterday that when the body is moving, then its mass becomes more, and more is the velocity, the more is the mass. So the body has the minimum mass when it is at the rest. So let us say that the body is at rest and its rest mass is m0, and now a force is exerted on that. And because the force is exerted, then what happens is it will start moving, and depending upon how long the force is exerted, it will attain a particular velocity. So let us say that after some time, it attains the velocity vector v, and at that moment mass becomes m. So we have body whose rest mass is m0, force is acting on that, and because of that force, it attains the velocity, and when it attains the velocity vector v, the corresponding mass is m. So we have this formula, m equal to m0 divided by root of 1 minus v square by c square. Okay, now let us apply the Newton's second law. Since the body is moving, you can apply the Newton's second law. So the body started moving because of that force. The force is F, vector F, and by Newton's second law, the force is rate of change of momentum. So d vector P divided by dt. Then we know that P equal to mv. P is the momentum. P is mass into velocity. So m into v. But here we are considering now the Einstein theory of relativity. So in Einstein theory of relativity, mass is also variable. So in this case, because of the force, the velocity is changing, also mass is changing. Both are variable. So when you differentiate this with respect to time, we have to differentiate m as well as v, because both are varying. That is according to the theory of relativity. So a derivative of the product. So first quantity m, derivative of second quantity dv by dt, plus second quantity into derivative of the first quantity dm by dt. But dv by dt, rate of change of velocity is acceleration. So m into vector A plus v dm by dt. So this expression we have found. Force equal to mass into acceleration plus v dm by dt. And in fact here itself we see that the force depends upon acceleration as well as the velocity. And that means the direction of the force will be according beside acceleration, it also depends upon the velocity. So here in this equation 1, F equal to ma plus v dm by dt, we see that the direction of force does not entirely depend upon acceleration, but it also depends upon the direction of the velocity. So that is what in the Einstein's relativity, the force and acceleration may not have the same direction. It can have the different direction. It is contradictory to the Newtonian relativity where force equal to mass into acceleration. That is Newtonian relativity. Their mass is constant, but here mass is variable. Because of that, we get one more term, vector v dm by dt. So the direction of force depends upon acceleration as well as velocity. So direction of force may not be same as acceleration. Then here we try to simplify this further. We will find out what is dm by dt. M vector A is there. dm by dt we will find out. Now to find out dm by dt, we consider that expression for total energy we have derived yesterday. E equal to m naught c square plus E suffix k. E suffix k is a kinetic energy. E suffix k is a kinetic energy and m naught c square is what is called as the rest mass energy. So what happens is even when the body starts moving, it has an energy due to its mass. Virtue of mass it has energy, and beside it virtue of the motion it has energy. Because the virtue of its mass, that energy is rest mass energy, and because the virtue of the motion, that is a kinetic energy. Now this is a total energy the body possesses. So this is a, see in the Newtonian relativity, the energy is kinetic energy. But here the total energy is it's because of virtue of its mass and because of the motion. Then we have shown that E equal to mc square. E equal to mc square. M is that final mass. So mc square equal to m naught c square plus ek divided by c square throughout. So what you get is m equal to m naught plus ek by c square. Now differentiate this with respect to time. Now m is a variable, so it becomes dm by dt. M naught is a constant. It is a rest mass energy. When it is at rest, it has some constant energy. So derivative of m naught is 0. Then 1 by c square is constant. Now this ek is variable because as the body is moving, the velocity may increase or it may decrease. But velocity varies. So kinetic energy also varies. So it is dek by dt. So finally what you get is dm by dt equal to 1 by c square dek by dt. That is equation 2. And now we can substitute this in the equation 1. And we can get the expression for the force. So this is what I have written here. F equal to ma plus v dm by dt and dm by dt equal to 1 by c square plus dek by dt. Now here dek is a change in the kinetic energy. See initially it was at rest and when it attains certain velocity, it will have some kinetic energy, difference of that. So the change in kinetic energy. Now this the body gains the kinetic energy because the force is acting, and because the force is acting, work is done, and work done is in terms of vector relation, vector f dot dr, force into displacement. So we write in vector form f dot dr. So we substitute this in equation 2, and equation 2 is dm by dt 1 by c square dek by dt, and dek is f dot dr, and here 1 by c square vector f dot dr by dt is a velocity. Rate of change of that in fact is a position vector, vector v, and this we substitute in the equation 1 for dm by dt, and what you get here is the vector f is there, vector m vector a is there, substitute for dm by dt 1 by c square f dot v. So m into a equal to f minus vector v 1 by c square f dot v. Now this is one quantity, and so therefore here we get acceleration as F by m equal to V 1 by mc square F dot V. So now here we see that acceleration and force does not have the same direction. It depends also on the direction of the velocity. So in except in the two situations, only in the two situations, two cases, both of them will have the same direction. Force and acceleration will have the same direction. But otherwise, in all other cases, it will have the different direction. Because in expression for A, vector F is there and vector V is there. So now let us consider these two cases where force and acceleration have the same direction. So case 1 we take, the force is perpendicular to the V. The direction of force is perpendicular to the velocity. Direction of the force is perpendicular to the velocity. Then here, this F dot dV, F dot V. See, F dot V is Fv cos theta. Theta is angle between F and V. So theta is 90 degrees, cos 90 is 0. See, F is perpendicular to the V, so the dot product is 0. So second term doesn't remain. So vector A equal to F by m, F by m. So here we find that acceleration and force have the same direction. See, vector A equal to vector F by m. So m has no direction. It is scalar quantity. So the direction of A is same as direction of vector F. So this is one case when force is perpendicular to V. Then we write this F equal to ma. See, from here F equal to ma, and we know that m equal to m naught divided by root of 1 minus v square by c square into A. Now F and A has the same direction. Now in this case, this mass m naught by root of 1 minus v square by c square. Now this mass is due to when the force acts perpendicular to the direction of motion, and corresponding mass is called as a transverse mass. So this corresponding mass is called as a transverse mass. So it is behaving like a Newtonian relativity. So when a force is acting perpendicular to the velocity, and then what happens is the force and acceleration has the same direction. So this is called as a transverse mass. Then next, second case, when the acceleration force has same direction is vector F is parallel to V. That means angle between them is 0. So A dot D is AB cos theta. AB cos 0. Cos 0 is 1. So here F dot V is equal to FV. We get like this. And then you take the magnitude of this. When you take the magnitude of this, you get like this. A equal to F by M minus V 1 by MC square FV. So take that F by M outside, 1 minus V square by C square. So this is acceleration. And this F equal to, so when you simplify this, F equal to MA by 1 minus V square by C square. Now this M equal to, we substitute that, M naught by root of 1 minus V square by C square. And now we write it as M naught A divided by 1 minus V square by C square raised to 3 by 2. So in vector form, this has no direction. M naught by 1 minus V square by C square raised to 3 by 2 has no direction. So vector F is written as vector A. So vector F and vector A have the same direction. So in this case also, acceleration and force has the same direction. Now corresponding mass, that means the multiple of that vector A is M naught by 1 minus V square by C square raised to 3 by 2. Now this mass, when the force act parallel to direction of motion, is called as the longitudinal mass. Longitudinal means parallel. Transverse means perpendicular. So these are the two cases when when the force and acceleration have the same direction. But see, not like a Newton relativity. Here what happened? Corresponding mass is also different. Value of the mass is different. See, this is raised to 3 by 2. So this is called as the longitudinal mass, and previous one is called as a transverse mass. Okay, so this is about the longitudinal mass and transverse mass. Then next we go to what is called as a twin paradox. Twin paradox. Now the meaning of the paradox is, see, the meaning of the paradox. The paradox means, suppose you are dealing with a certain concept and you are explaining that concept by using a valid reason. Suppose some concept is there, you are using a valid reason to explain that concept. But what happens is the result is contradictory. Then it is called as a paradox. Okay, so you are arguing correctly, but it gives a result contrary to your concept. Then it is called as a paradox. So here a twin paradox. This twin paradox come across in the what is called as a time dilation. I mentioned that. See, the time interval measured when this time interval between the events measured when that event is at rest is the less than the time interval measured between the events when that event is moving. Now, when the event is moving, then the time is more, and when the event is at rest, the time is less. Okay, so this called a time dilation. Time is more. See this, if you use this formula, delta t equal delta t suffix 0 root of 1 minus v square by c square. See this v square by c square is a quantity less than 1. So you are dividing the quantity by number less than 1. So resultant quantity is bigger. So delta t is greater than delta t naught. This delta t suffix 0 is a time interval when it is at rest, and delta t is a time interval spent in that event when it is moving. So delta t is greater than delta t naught. So time interval is longer, that means it is slower. So it's called as the slowing down of the time. And sometime back I had mentioned about one example. See, I had mentioned about one example where there are friends who are of the same age. I had mentioned something like 17 years, and one of them, he goes with the speed of the light or very high speed, very close to the velocity of the light, and when he comes back, he is and for him the 5 years have passed, but and he becomes this 17 plus 5, that is 22 years. But those who are there on the earth at rest, they become 65 years. Okay, so what happens is, any body moving close the velocity of the light, the time slows down. Okay, time slows down. That is called as a time dilation. Now, if you use the theory of relativity, that means if you use the Lorentz transformation, see there are two frames, the S and S dash. Okay, S and S dash. Now here what happens is, S dash is moving away from S with velocity v. So let us say that this v is very large. Suppose there are twins. So there are twins. Twins means they will at any time they will be of the same age. Then if one one twin is in the frame S, that means that frame is at rest, and other twin is in the frame S dash. So it may be in some spacecraft. It is moving very fast, with a very high speed, close the velocity of the light. So when it goes away, according to that concept of time dilation, the twin in the second frame will be younger than the twin in the first frame. So after some time interval, so the twin in the second frame will be younger because there is a time dilation, slowing down at the time. So he will be younger for his sibling in the first frame. Okay. Now, if you look at this, if you use this mathematics, suppose someone is in the frame S dash, you will see that this first frame is going away from him. Suppose someone S dash is at rest. So someone is in frame S dash, you will see that frame S is moving away from him. And suppose that one of the twin is in the frame S dash, other twin is in frame S. So now frame S is moving with very large speed, very close to the velocity of the light. So there is a time dilation here, and then what happens is the twin in the sibling in the second frame, we'll see that his sibling in the first frame is younger. Okay, so now here in the first case and second case, the sibling in the first frame, we'll observe that the sibling in the second frame is younger. Whereas, if you consider the second case here like this, the sibling in the second frame, we'll see that the sibling in the first frame is younger. So this is a contradictory result. Say we used a proper physics here, proper physics and proper mathematics in both the cases, but we get a contradictory result. So in the first case, the second twin appears to be younger, whereas in the second case, the first twin appears to be younger. So this is called as a twin paradox. So it is a paradox also. If you apply your mathematics and physics to this case, then it is a paradox because it gives contradictory result. So if you consider one case, what you consider is correct. So one of the sibling is remains younger, whereas in the second case, another sibling becomes younger. Okay, actually both are. We have said that both are one and the same. Whether this is moving away from here or this is moving away from the second frame, it is one and the same. But it gives a contradictory result. So this is called as a twin paradox. Okay, this is called a twin paradox. Okay. What happens is there's nothing wrong with the time dilation. It's correct. Experimentally, they have verified. So experimentally, the time dilation is verified. So I mentioned about the radioactivity. They put the radioactive sample to rotate on the disk with very high speed. They found that this half-life becomes longer. Okay, so there is a time dilation. Even similarly, they have found that these elementary particles. See, elementary particle has some lifetime. It has some lifetime, and when they produce this, say what happened is one elementary particle is transformed into another. So that elementary particle has transformed from the another particle. So the time interval between which that elementary particle remains of the same type, that is called as a lifetime. They have found that in the laboratory, that means when it is at rest, so that elementary particle is at rest. So time it is formed and time it gets changed to another one. That time interval, is shorter than the time interval measured in the elementary particle in the cosmic rays, which where elementary particle is moving. So there is a time dilation. So the time dilation is experimentally verified. But if you try to analyze that this time dilation using this frame of references, Lorentz frame of reference, there is a paradox. It gives a contradictory result. So this is what is called as a twin paradox. Now, one more thing I mentioned, forgot to mention yesterday, that mass, say this mass m equal m naught by root of 1 minus v square by c square. Higher the velocity, the more is the mass. Suppose the body moves with the higher velocity, more is the mass. In fact, this concept is you will have come across in the study of the cyclotron. In the cyclotron means what? The particle is made to move in a cyclic path, and the purpose of the cyclotron is to give a large energy to the particle, and the energy of that particle depends upon the radius of that cyclotron. Larger the radius, then it will gain more energy. But what happens is, there is a limit for that, because in the formula for energy, the mass is there in the denominator. See, in the formula for the energy, mass is there in the denominator. And what happens is, when the velocity of the charged particle becomes very large, the mass becomes large. So what happens is, since the mass is in the denominator, the energy will get decreased. So because of velocity, energy increases. Because of the increase of the mass, the energy decreases. So in the cyclotron, there is a limit. You cannot increase the charge particle to very, very large velocity, large energy. So there is a limit. Okay. So all this, the reason for telling you this is, all these concepts in the relativity are used in other branches of the physics. I had mentioned from time to time. This is example. This is used in a cyclotron, and many other examples I had given where it is also used, or it is required to be used in the other branches. A Compton's effect, you require the relativity. Now, for in a study of the motion of the heavenly bodies, everywhere you require the concept of the relativity. Okay, so with this section on the relativity is completed. Okay, so I'll stop here and I will continue tomorrow with the first section, which is electromagnetic theory 2, and which deals with the magnetostatics. So that we will take up tomorrow. So thank you very much.